Hi everyone, welcome to Nithin Academy and I'm Nithin. And there are many things new in this chapter, so keep your eyes and ears open. And today in Secondary 1 Science, I will be moving on to the next chapter, Particulate Nature of Matter. Okay, so let's dive straight into it. Okay, for the first segment of this video, I'll be going through what is the particulate nature of matter. Okay? So what is the particulate nature of matter? So basically, let's have an example over here. So dust particles do not move on their own, right? So air, like any other matter, consists of tiny particles. Okay, it consists of tiny particles, which is air. Okay, all the particles of matter are constantly moving in a random manner, and this is known as Brownian motion. Okay, the constantly moving air particles, okay, air particles are constantly moving, right? They collide with the dust particles, and hence the dust particles are observed to be moving randomly. So due to the collision of air and dust particles, the dust particles seem like they are moving around randomly. Okay, so the particulate nature of matter can be used to explain this. Okay, so let's just have a quick look. So imagine these are the air particles. Okay, so we have a lot of air particles here. Okay, and we also have dust particles. Okay, so what happens is that these air particles actually collide with the dust particles, and the dust particles also collide with the air particles. Understand? So I hope you understood that. And without this collision, right, the dust particles actually do not seem to be moving. Okay, it's because of the collision of the air and dust particles colliding with each other that the dust particles seem to be moving around. Okay, so I hope you understood this. Okay, okay, next, what is Brownian motion? So I just mentioned a new word, Brownian motion, right? So what is Brownian motion? So under a microscope, okay, under a microscope, why are the pollen grains suspended? So this is a pollen grain, okay, over here. See this big red color dot? So that's a pollen grain. So why are the pollen grains suspended in still water observed to be moving even when there's no presence of wind? Okay, so basically the same concept applies from the dust particles. So basically the water particles collide with the pollen grain, and the pollen grain also collides with the water particles due to the water particles colliding with the pollen grain. So I hope you understood that. So the random movement is known as Brownian motion. Okay, the random movement, in honor of Robert Brown. So Robert Brown is the one who actually found out this phenomenon. Okay, so where there are microscopic particles suspended in a liquid or gas. Okay, so Brownian motion is actually the random movement in honor of Robert Brown, where microscopic particles are suspended in a liquid or a gas. Okay, so you can see that water is actually a liquid, and before this dust particles was actually in a gas, air. Okay, so I hope you understood that. So you can see the phenomenon of Brownian motion by Robert Brown. Okay, first of all, the water particles are always moving randomly around. However, they are invisible to the naked eye. So the water particles are actually always moving around, right? But we can't see them with our eyes. Next, the water particles collide with the pollen grains that are actually visible to the naked eye. So we can actually see the pollen grain but not the water particles. Okay? Hence the pollen grains appear to be moving on their own, although it is actually the collision between water particles and the pollen grains. Okay? So I hope you understood that. Now let's move on. Okay, next off, we need to know the three main principles. So the first principle, Okay, so let's just write that down. First principle, all matter is made up of small discrete particles. Okay, so all matter is made up of small discrete particles. All matter. Okay, so this is important. Okay, secondly, we have all particles of a pure substance. Okay, so all particles of a pure substance are identical. Okay, so that's number 2. Next, we have number 3, the last principle. Okay, so particles of all matter are in constant, okay, or random motion. Okay, so particles of all matter. So I hope you understood that. So these are the 3 main principles of Brownian motion. Okay, so I hope you understood that. Now let's move on. Okay, for the second segment of this video, I'll be going through how can we explain the properties of different states of matter using the particulate nature of matter. Okay, so that's a lot to take in, right? So let me read that out again. So how can you explain the properties of different states of matter, so different states of matter, using the particulate nature of matter? Okay, so I hope you understood that. So how can we do that? So first of all, let's take a look at what is matter. So matter is actually anything that has mass and takes up space. I hope you all remember this definition from primary school, because this is actually a really important definition that you're supposed to remember. So if you don't remember, please go revise up on matter. Okay, and it can be grouped based on its states. So basically there are 3 states of matter, right? Solid, liquid, and gas. So if you are using water, right, for example, water can actually exist in 3 different states. Ice is basically solid state, water is basically liquid state, steam or water vapor is actually gaseous state. Okay, so I hope you understood that. So however, all the states of water should consist of the same type of particles since they are chemically the same. Okay, so this is something important that you should know. So all states of water, whether be it ice, water, steam, water vapor, they all consist of the same type of particles. Okay, since they are chemically the same. Okay, so I hope you understood that. So these are basically the states of matter. So as you can see, this is actually ice, right? And this is water. And this is lastly steam or water vapor. Okay, so I hope you understood that. Now let's move on to the next part. Okay, particulate model of a solid. Okay, so basically particulate model of a solid. So we are going to check out about this. Okay, so there are some properties that we are going to look at it. Okay, so first of all, let's take a look at the nature of particles. So there are 4 types. There are basically 4 segments separated for the nature of particles. Basically, first off being forces of attraction between the particles. So in a solid, okay, so forces of attraction between particles. Okay, so remember, in a solid, they are actually held together by very strong forces of attraction. So that's why okay, sorry. So that's why you can see that they're actually very close to each other, all the particles. Can you see that? I hope you can see that. You can see that, right? You can see how closely they are connected by each other, right? So after drawing that, I hope you understood like how close and how compact they are. They are basically connected to each other. This is because of the very strong forces of attraction. Okay, and what does the physical property mean because of them having a very strong forces of attraction? Basically, it means that they have definite volumes. Okay, so this is quite important. It means that they have definite volumes. Okay, next, movement of particles. So this is the second part of nature of particles. So their nature is basically the movement of particles. In a solid, they actually vibrate about in their fixed position, constantly unable to move about freely. Okay, so do you remember the third principle of particulate nature of matter? All particles are always in constant or in random motion. Okay, so solids, right? You might think, oh, so this pen is a solid, doesn't move around unless you make it move around, right? No, but the particles in this pen are actually constantly vibrating around. Okay, so I hope you understood that. So the movement of particles. Okay, so they actually vibrate about in their fixed position constantly, unable to move about freely. So this is why this is actually the result of the very strong forces of attraction. They actually vibrate about in their position, but they can't move about freely because of the very strong forces of attraction. Okay, so I hope you understood that. Okay, next off. Okay, next off we have the setup of particles. Okay, setup of particles. So the setup of particles basically meaning their arrangement. Okay, arrangement. So basically solids, the particles are actually arranged in a fixed regular pattern. Okay, fixed regular pattern. So this means that solids actually have definite shapes, and I hope you have like found out something, that you see this physical properties over here, right? These physical properties are actually something that you have already learned in primary school. Okay, but all of this, right, is actually something that you're learning in secondary school. So this is so physical property. So this is basically the explanation of the physical property. So I hope you understood that. Okay, so nature of particles and the description is basically the explanation of the physical properties, okay, of solids, liquids, or gases. So I hope you understood that. Okay. Okay, so now that we are done with the third one, let's move on to the fourth one, the last one. Okay, so last one is basically the distance between the particles. Okay, so the particles are actually packed very closely because of the strong forces of attraction again. So they're actually packed very closely together and they cannot be compressed. Okay, so I hope you understood this. Now let's move on to the properties, the particulate model of a liquid. Okay, so now let's take a look at the particulate model of liquid. Okay, so first off, let's take a look at the nature of particles, basically the forces of attraction between the particles. So in a liquid, they are held together by strong forces of attraction. So even solids are attracted together by strong forces of attraction, right? But for liquids, there's something different. The force of attraction, right? Force of attraction is not as strong as solids. Okay, so this is something that you need to take note. Okay, so the forces of attraction is actually not as strong as in solids. Okay, so that's something that you know. And since they are held together by strong forces of attraction, this means that they have definite volumes. Okay, next up, the movement of particles. So the movement of particles is basically that the particles slides past one another and moves randomly, unlike the solids, which are packed closely together and they are arranged in a fixed regular pattern. So liquids are actually a bit more free to move around, and they move around freely, move randomly, and they slide past one another. Okay, so I hope you understood that. Okay, and for the physical property, there is no physical property for this one. Okay, next, set up of the particles. They are arranged in no fixed or regular pattern. Okay, so this is the setup of particles. They are arranged in no fixed or regular pattern, and this means that they have no definite shapes. Okay, liquids actually do not have definite shapes because they take up of the object that they are in. Okay, so if for example I have a beaker over here, right? So if I have a beaker over here, I pour water, the water is going to take the shape of the beaker. But if for example, if I have a conical flask over here, right, the water is actually going to take the shape of the conical flask. So you can actually see the difference. Okay, so let me just draw the beaker and conical flask clearly. Okay, so this is the beaker and this the conical flask. Okay, so I hope you understood that. So you can see that it's a different shape, right? So let me just highlight to you which is the shape. So this is actually the shape of the water, while this is the shape of the water in a conical flask. So this means that liquids actually do not have a definite shape. Okay, so I hope you understood that. Next off, lastly, basically the distance of particles between the particles. So liquids are also packed very closely together, but not as close as solids. Okay, so I hope you understood that. And this means that liquids cannot be compressed as well. Okay, lastly, let's move on to gas. Okay, gas. Okay, so here we have the particulate model of gas. Okay, so let's take a look at the nature of particles first of all. Forces of attraction between particles. Okay, attraction between particles. So let's take a look at that first. So they are held together by weak forces of attraction. So as you can see that, as you can see over here, the particles are actually far apart from one another, right? So let me just show you how far apart they are. So you can see that it actually takes twice the distance of a liquid to go itself. So you see how far apart they are, right? See that they are actually quite far apart from each other. And this shows that gases actually do not have any definite volume. Okay, so they have no definite volumes, and the movement of particles. Okay, the movement of particles. Actually, for gases, right? They are actually the particles actually move around randomly at high speeds. So, for example, like air, right? The particles actually move around randomly at high speeds. Okay, so I hope you understood that. And the setup of particles, there is no fixed nor a regular pattern in this because they're actually really far apart from each other, and they have very weak forces of attraction. Okay, and this shows that they have no definite shapes as well, just like liquids. Okay, and the distance between the particles. So this is something that you don't need to know already, because we can tell that the distance between the particles is actually really big. So the particles are far apart from each other, and this means that gases can actually be compressed. Okay, so do you understand why? So imagine if I have a syringe over here. So let me just draw a syringe. Okay, so imagine if I have a syringe over here, and this is the plug to push it in. Okay, to push it in. So imagine there are actually gas particles like this. Okay, So if I push in the gas particles, right, they actually can be compressed because there's actually a lot of space between each of them. Okay, so if I push it in, right, so let me just show you a version where it's pushed in. So if I pushed it in, right, the space between the gas particles will actually go away, and all the particles will come together very close together, and the syringe will be like this. Understand? So this is how like gas particles actually be compressed. So I hope you understood that. So now let's move on to the next part. Okay, so for the third segment of this video, I'll be going through how does particulate nature of matter help us to explain the behavior of the particles upon heating and cooling. Okay, so let me just read that off one more time because there's actually a lot to take in. So how does the particulate nature of matter help us to explain the behavior of particles when upon, basically meaning like when they are heated or cooled. Okay, so let's just take a look at that. So upon heating and cooling, so behavior of the particles. So how does the particles actually react to these kind of things? Okay, so now let's take a look at it. Okay, so there's actually expansion when heated, so let's take a look at that first. So this is a solid first of all. So from a solid, upon heating, it becomes a liquid, right? So it actually does not become a liquid, it just becomes bigger, it just expands. Do you know why? Because when heat is applied, the particles actually move more faster, more vigorously, and the forces of attraction are actually becoming slightly weaker, and this actually opposes the forces of attraction, and it actually expands. Okay, so let's take a look at that in the actual explanation terms. Okay, first off, when matter is heated, the particles gain energy and vibrate more vigorously. So they gain heat energy, right? But you can't say gain heat energy. You can only say gain heat or gain energy, okay? So I hope you understood that. So they gain energy and vibrate more vigorously. The particles move faster and slightly further apart from one another, causing the volume of the matter to increase. So since so from a solid like this, right, they actually moved apart. Okay, and now the solid is actually this big, and so this means that it has a bigger volume, right? Yeah, so this is what I mean. Okay, so I hope you understood that. The matter expands. This process is known as expansion. So this is the process of expansion uh, when particles are actually, the behavior of particles when they are heated. Okay, so basically when matter is heated, the particles gain energy and vibrate more vigorously, and the particles move faster and slightly further apart from one another, causing the volume to increase. The matter expands. This process is known as expansion. So I hope you understood this. Now let's move on. Okay, next off, contraction. So from here, contraction when cooled. Okay, so from big, upon cooling, actually becomes smaller, right? So this is actually called contraction. So when matter is cooled, the particles lose energy and vibrate less vigorously. Okay, so it's basically the opposite explanation of expansion when heated. Okay, so the particles move slower and closer to each other, causing the volume of the matter to decrease. The matter contracts. This process is known as contraction. So let's take a look at that really. So for expansion, when the matter is heated, right? So no, when the matter is cooled, the particles lose energy. But for expansion when heated, right, is basically gain energy, vibrate less vigorously for this. But for expansion when heated, is vibrates more vigorously. The particles move slower and closer to each other. But for expansion, right, is basically move faster and further apart from each other, causing the volume of the matter to decrease for cool. But for heat is basically causing the volume of the matter to increase. The matter expands. This process is known as expansion for expansion, and the matter contracts. This process is known as contraction for contraction. So when I said that, right, that will be a bit confusing to you. So let me just read this one last time. So when the matter is cooled, the particles lose energy and vibrate less vigorously. The particles move slower and closer to each other, causing the volume of the matter to decrease. The matter contracts, and this process is known as contraction. So I hope you understood that. Now let's move on. Okay, so there's something that you need to take note of. So the number and size of particles in matter do not change during expansion or contraction. So they do not change. So look at this. So there's actually 1, 2, 3, 4, 4, 8, 12, 16. 16 particles here, right? And there's also 1, 2, 3, 4, 8, 12, 16 particles here. So the number of particles do not change, nor do the size. So the size actually remains the same as well. Okay? So what does change? So the only thing that changes is actually the space between the particles. So you can see, right? So let me just show you. So let me erase this over here. And let me show you. So the space between the particles actually change. So here you can see the space between the particles, right? So you can see the space between the particles, right? They're actually very close to each other. Okay? Okay, so they're actually very close to each other, the space between the particles. But for after expansion, right? Or before expansion, right? They actually, so after expansion, the particles space is actually quite large, as you can see over here. See that the gap is actually much bigger than the gap over here, right? So I hope you can see that, and thus I hope you understood that the size and the number of particles do not change, but the space, the gap, the space between the particles actually change. And something else you need to know, there's actually a conservation of mass. The mass of the matter does not change. Okay, only the volume changes. The mass does not change at all. Okay, so I hope you understood that. Okay, now let's move on. Okay, so for the fourth segment of this video, I'll be talking about the change in state and heating and cooling. Okay, change in state with heating and cooling. Okay, so let's talk about that. Just changes of state of matter. So these are the three states of matter: solid, liquid, and gas. And this is how they actually look in particle form. Okay, so I hope you understood that. So matter can exist in solid, liquid, or gaseous state depending on its melting point and boiling point. Okay, this is something important. Depending, so it can exist in three states depending on its melting and boiling point. Okay, next, at a fixed pressure, the temperature of an object will determine its state. Okay, so when the pressure on the object is fixed, right, the temperature of that object will determine its state. Okay, next off, examples of changes of state of matter: so melting, freezing, boiling, and condensation. So we're going to take a look at these four changes in state right now. Okay, so I hope you understood that. First off, let's take a look at melting. Okay, so what is melting? Melting is the process in which a solid changes into a liquid without a change in temperature. Okay, so that's melting for you. So let's take a look at it. So from a very closely packed strong forces of attraction to a very gaseous feeling. Okay, liquidish. Okay, so you can see how the space between the particles change, and how the speed and how the freely moving movement of the particles actually change. So you can see that at first it was a solid, right? Actually very packed very closely to each other. The forces of attraction are very, very strong, and it can't move freely. It just vibrates about in its fixed position. Okay, well, slowly when it gains heat, it starts melting, right? And then actually so imagine, let's just take this as water. Okay, so in solid state is ice, right? Melting state is water, right? So in water, right, it actually moves around very freely, slides past one another, right? And they're actually still held together by very strong forces of attraction, but not as strong as the forces of attraction in a solid ice. Okay, so this is basically using the properties. Okay, so I hope you understood that. Now let's take a look at the explanation of melting. Okay, first off, when a solid is heated, the particles gain kinetic energy and vibrate faster about in their fixed positions. Okay, when particles gain enough energy, they overcome the very strong forces of attraction between them. Okay, the particles start to slide over one another, the solid melts and becomes a liquid. So this is actually a model answer. Okay, so this is actually a model answer. So please do take note of this, and please do understand this answer, and don't try to memorize this. Okay, you can memorize it, you should memorize it, but when you memorize it, don't memorize it blindly. Okay, you should memorize it with the understanding in it. Okay, without understanding this, you can't apply this to real life situations. So basically, in most secondary school science exams, right, they actually will you will heavily test you on applied questions. So basically like application based questions. So when a solid gains heat, so when you put the solid in when you put ice in slightly warm water, right, what happens? So this is application basically. So you can you must state this answer over here, but you must understand it. If they just blindly ask you explain the process of melting, then you can just you don't even need to understand this in order to say anything. But most of the questions are application based questions, so please do take note that you should understand this fully before you go through before you like even start writing it. Okay, so I hope you understood this. Okay, so let me just go through it one more time, so because this is really, really important, and the rest of it will revolve around this template actually. Okay, so melting, freezing, boiling and condensation will actually revolve around this template, around the same. Okay, so when a solid is heated, the particles gain kinetic energy. So what is kinetic energy? You've learned this in primary school. Kinetic energy is basically movement, right? So how fast the object moves. So they gain kinetic energy, meaning that they will actually vibrate faster about in their fixed positions. Okay, when the particles gain enough energy, they overcome the strong forces of attraction, because in solids there are actually very strong forces of attractions, right? So they actually overcome the strong forces of attraction between them, and the particles start to slide over one another. Okay, and the solid actually melts to become a liquid. Okay, so I hope you understood that. Now let's move on. Okay, second off, let's take a look at freezing. So freezing, let's take a look at what does freezing mean. Freezing is basically the process in which a liquid changes into a solid without a change in temperature. Okay, so freezing is also done in 0 degrees Celsius, just like boiling, just like melting, I mean, sorry. Okay, so I hope you understand that, and this template is actually going to be the opposite of melting. So let's take a look at it. Okay, so it's basically the opposite of melting, as you can see, right? So as you can see, it's like from a very uh from like the space between the particles are actually like quite large, right? And they become closer and packed more closely to each other, becoming from a liquid to a solid. Okay, so When a liquid is cooled, okay, let's take a look at this. So when a liquid is cooled, the particles lose kinetic energy and move more slowly. When the particles lose enough energy, they cannot overcome the forces of attraction between one another. The particles start to move closer to one another and vibrate in their fixed position. The liquid freezes and becomes a solid. So this is basically the total opposite of melting, okay? So I hope you understood that. So now let's move on. Okay, boiling. Boiling is actually the process in which, okay, so let's take a look. Boiling is actually the process in which a liquid changes into a gas without a change in temperature. Okay, so when a liquid is heated, the particles gain kinetic energy and slide around more vigorously. Okay, when the particles gain enough energy, they overcome the strong forces of attraction between one another. Okay, so when the particles gain enough energy, they overcome the forces of attraction between one another. Okay, the particles break free from one another and move faster and further apart from one another in all directions. Okay, the liquid boils and becomes a gas. So this is how you explain boiling. Okay, so let's go through it one more time. When the liquid is heated, the particles gain kinetic energy and slide around more vigorously. The particles gain enough energy and overcome the strong forces of attraction between one another. Okay, they break free from one another and move faster and further apart from one another in all directions. So basically they move further apart in all sorts of directions. Okay, so the liquid basically boils. So you know when a liquid boils, right, there's actually a lot of air bubbles coming out. And so these air bubbles actually coming out state that the liquid is actually boiling, and you can see that the water is actually moving very rigorously while it is boiling, right? So it boils, and this water actually changed into a gas. Okay, it becomes a gas because of that. Okay, the particles actually go further apart from each other, and the forces of attraction actually becomes weaker, and thus it changes into a gas. Okay, so I hope you understood that. Okay, lastly, condensation. Okay, let's take a look at what condensation is. Condensation is the process in which a gas changes into a liquid, or a gas changes into a liquid without a change in temperature. Okay, when a gas is cooled, the particles lose kinetic energy and move more slowly. Okay, basically the opposite of boiling. Okay, when the particles lose enough energy, they cannot overcome the forces of attraction between one another. The particles start to move closer and start to slide over one another. The gas condenses and becomes a liquid. Okay, so when a gas is cooled, the particles lose kinetic energy. Okay, they lose kinetic energy and move more slowly. Okay, when the particles lose enough energy, they cannot overcome the forces of attraction, so they actually start to move closer and start to slide over one another. Okay, and actually the gas condenses and becomes a liquid. Okay, so I hope you understood that. Now let's move on. Okay, so for the fifth segment of this video, I'll be going through how does the temperature affect the rate of the movement of the particles. Okay, so this is actually the last segment of this video. So let's take a look. How does the temperature affect the rate of movement of particles? Okay. Okay, so there's something new over here. Okay, so you're going to learn something called diffusion. So diffusion is actually the net movement of particles from a region of higher concentration to a region of lower concentration. Okay, so this is basically, so imagine this is actually, all these particles are actually sugar particles. Okay, imagine these are the sugar particles. Okay, and imagine this is a beaker and this is the top of it. Okay, top. Okay, wait, sorry. So imagine this is the like a mug, and all the sugar particles are actually on this side instead of this side. So diffusion, right, is actually uh after time, right, after some time, right, the particles from this side will actually come out to this side to make it even. So the amount of particles on this side will be equal to the amount of particles on this side, okay, or else like at least about the same, okay. So now that you have learned about diffusion, right, the net movement of particles from a region of higher concentration to a region of lower concentration to even it out. Now let's take a look at this question: how does temperature affect the rate of movement of particles? So when the temperature increases, the kinetic energy of all the particles has increased. Therefore, at a higher temperature, the rate of the fluid, liquid or gas, and particles will diffuse faster at the lower diffuse faster than at a lower temperature. Because the particles start moving faster, it is easier for it to move faster to the other side, right? Or when the temperature decreases, the particles actually move closer to one another, and actually takes a very long time to diffuse and be even, right? So I hope you understood that. And with that, I've come to the end of the video. Okay, thanks for watching, everyone. I hope you have enjoyed this video and understood more about secondary one science, the 7th topic of particulate nature of matter. And I hope this video really helps you. And if you're not subscribed to Nithin Academy, please do subscribe and be a part of our family. Thank you and bye bye. I'll see you again in our next video. Bye.